Hello team. This video is going to be examples for AC power factor. Okay, so hopefully you've already watched the lecture video on AC power factor. This video here we're going to go through. There were 6 example questions at the end of that PowerPoint. So we're going to go through those 6 examples. I've added another 5 examples on top of that. I've done all the working out, I've done all the maths, I've put it into one single document here, and hopefully by the time we've gone through this, you will understand this stuff pretty well. It's taken me quite some time to put this together, and I think I've seen enough of this to last me a lifetime, but I tell you what, I feel like I know it inside out, so hopefully you will as well. This document that we're going to go through now will be available on the Canvas page. If you go to the Canvas page for AC Power Factor, you'll find a link for this document, so you can open that and follow along on the video if you want to. I'm going to have this document up, so it might be beneficial for you to have that for yourself. Certainly when you go through the practice examples yourself, good idea to have this document open so you can sort of refer back to the equations and the working out that we've used. On the first page here, you can see that I've added a page with just the abbreviations here, just so if I do refer to something that you're not sure about, here it is. It's written in here. For example, reactive power is Q, and we're using kVAR or VAR to refer to Q, and so on and so forth. Next to that, in this column here, I've got all the formulas that I will use throughout the document. So this will be the front page you can refer back to at any time, obviously. If you're doing your practice examples and you're thinking, oh, what was the formula? How do I work out the apparent power S if I have true power P and I have the power factor? Well, here it is here. S equals P over power factor. Apparent power equals true power over power factor. I've also, as I've gone through this document, I've written a few little notes in there as well, just on what I'm doing and why. So obviously I'll explain it as I go through the video, but then if you need to refresh your memory, you can refer back to the document. Hopefully my explanatory notes will mean that there's enough information there that you don't have to go back and watch the whole video again. But of course the video will be available for you to go back to. Okay, so let's get straight into it then. So example number 1, this was as I said, these first ones were in the PowerPoint, so if you're looking for them, that's where I've got them from. So our first example is in a series RL circuit, RL meaning resistive and inductive. So R for resistance, L is induction, remember. In a series RL circuit supplied with 50 volts, the current is measured as 100 milliamps with a phase angle of 25 degrees. Calculate the apparent power, true power, and reactive power in this circuit. Okay, so in order to work out apparent power is our total power, if you like. That's our input voltage multiplied by our input current. Remember that power is voltage times current. So S equals V times I. We're going to use the input power, the total power 50, and our total current measured as 100 milliamps, so 0.1 amps there. So that equals 5 volt amps, just volts times amps, so 5 volt amps is our power. Next, true power. We have to work out the true power of the circuit. There's multiple ways that we can do true power. If we look back up at the top here, we've got a multitude of different formulas that we can use. Apparent power times power factor. We can use Pythagoras. Remember that our power triangle, P is one part of our power triangle, so S being the hypotenuse of the power triangle, S squared minus Q squared, square root of that is P. We could also use Pythagoras, trigonometry to work out P, and that's what we'll do here. We're not given enough information to use Pythagoras. We don't know the only side of our triangle that we know at the moment is the hypotenuse, right? Because we've got 5 volt amps, that's what we worked out as S. We don't know anything else except that angle. But with the hypotenuse and the angle, we can work out the adjacent side, and the true power is always the adjacent side. So in this case, so that means we can use CAH, C-A-H, and that is, if we remember, cos of the angle, cosine of the angle equals the adjacent over the hypotenuse. In this case, the adjacent side is, as I said, true power. The hypotenuse is our apparent power, and then our angle is 25 degrees. That was given up here, 25 degrees. So cos of the angle equals adjacent over hypotenuse. So that means cos 25 equals power divided by 5, 5 being our apparent power. So we rearrange that formula so that it is P, true power, equals cos 25 times 5. That means our true power is 4.53 watts. The next part of the question was work out the reactive power. And that's pretty simple because we use Pythagoras. We now have two sides of our triangle. We have the hypotenuse here, that's apparent power. We have the true power, which is the bottom, the horizontal side or adjacent side. And so Q equals the square root of S squared minus P squared. Nice and easy. S squared is 5 squared minus the P is 4.53. So that works out to 2.12 volt amps reactive, VAR, volt amps reactive. Now it's a good idea, I should have mentioned this at the start, but I think it's a good idea. You may have to pause and restart this video, that's fine, but as I go through each of these, follow along and do them in your calculator. One, just to get the idea of it, to, into practice of using the formulas, but also remember that sometimes, particularly when we're using things like this, our square root with 5 squared and 4.53 squared, etc., where you place the brackets will make a difference, or you may need to put brackets or you may not, depending on your calculator model. Now I know that most of you have had enough practice of this now to have some understanding of how your own calculator works and what you're going to need to do, but better to be safe than sorry. We certainly don't want to be going into the test and then figure out that our calculator doesn't work things out how we think it does, or even worse, you don't figure out that your calculator isn't working things out how it should, and you end up with all the wrong answers and you have no idea. So I think it would be beneficial for you to work through these examples with me. Actually pause when I go through that equation, put that equation into your calculator, make sure you're getting the same answer. Right. So when we do the test for this topic, we're also going to need to draw power triangles. So as we go through this video, I've constructed a bunch of power triangles. They're very simple. All I've done here, and this is all I will look for from you, is marking the side that is Q, your reactive power, the side that is S, apparent power, and the side that is P, the true power, and the angle. You need to draw the triangle to scale, so that means that the values of the side are scaled to the size. This triangle is not to scale. Obviously the P there, 4.53, should be twice as long as the Q, 2.12. I'm realizing now it's quite late at night. I've spent a lot of time on this. I've realized that I've constructed that triangle very poorly and I failed to go back and fix it. My apologies. The remainder of the document has much better to scale triangles. So let's move on. So we've got our three answers there. As we go through this document, you'll also notice that I've highlighted each place where it's asked us for an answer in the question. I've highlighted that answer as we go through. So we've got apparent power, true power, reactive power, 5 volt amps, 4.53 watts, 2.12 VAR. Question 2. A series CR circuit. So this time we have a capacitive and resistive circuit with a 230 volt 50 hertz supply, has a resistance, a resistor of 1.2 kilo ohms, so that's going to be 1200 ohms, and a capacitor, 20 microfarad capacitor. Calculate the apparent power, true power, and reactive power of the circuit. Also draw a clearly labeled power triangle associated with this circuit. Okay. So the first thing we're going to do is, it says there, work out the apparent power. Now, as I said here, our apparent power is going to be V times I. We have our V, that's 230 volts, but we don't have an I to go with it, so we need to find that out. So we need to find the current. Our current is going to be V over Z, Z being in this case our impedance, which is, so that's just basic ohms law. Remember, I equals V over R, Z is impedance, it's a type of resistance if you like. So our Ohm's law will tell us that I equals V over R, but we don't know what the total impedance is either, so we need to find that first. In order to find the total impedance, we'll use, if we think about our impedance triangle, remember that's essentially the same thing as our power triangle. The square root of R squared, that's our resistance, plus XC squared, the two sides of our triangle. So XC will be one side of the triangle, R will be one side of the triangle, and Z, the total impedance, will be our hypotenuse. So that's how we're going to work out Z. But in order to fill in that formula, we're going to need to find XC. We've been given the R, that's at the top there, 1,200 ohms, or 1.2 kilo ohms. But we don't know what the XC is. So we're going to have to go through these three steps before we can get to apparent power. And we should be familiar with this formula. XC equals 1 over 2 pi FC. So we know what our F is, and we know what our C is. Our F was 50 hertz, and our C was 20 microfarads. So we punch those into that formula. 1 over 2 times pi times 50 times, and I've put brackets here, 20 times 10 to the negative 6, because that 20 is the capacitance in microfarads. So we're converting their microfarads by going 10 to the negative 6. So that whole formula works out to 159.15. Again, please work that out in your calculator, make sure you're getting the same result. If you're getting a totally different result and you can't work out why, it's possible that I've got it wrong. It's pretty unlikely, but actually this is a pretty long document and I've done a lot of calculating and my brain is pretty fried at this point, so it's entirely possible that I've got one or two wrong. So if you really cannot get the same answer as me, please let me know. Okay, so that gives us an XC of 159.15 ohms. But then, as I said up here at the top, we can now find our total impedance. So our impedance is going to be square root of R squared plus XC squared, so 1200 squared plus 159.15 squared. This is just normal Pythagoras, right? Three sides of a triangle. Which means that our total impedance is 1210 ohms, or 1210.51 ohms rather. And now that we have our total impedance, we can work out our current. I equals V over Z. V is 230, it's our voltage, it was given at the start. Our Z is 1210.51 ohms that we just worked out, which gives us a total current of 0.19 amps. Now that we have our current, we've already been given our voltage, that means we can work out our apparent power. S equals V times I, so V being 230, I being 0.19 amps. If we go back up here, this whole document is 2 columns per page. So if you go down the left column here, down to the bottom, and then back up to the right hand column. So that means that formula there, 230 times 0.19 equals 43.7 volt amps. 43.7 VA is our apparent power. The next part of the question was true power. One of the formulas we can use for true power would be I squared times R. P equals I squared times R. We could use V times I, but remember it's a series circuit, so first we would have to work out what the actual voltage on that component is, what the volt drop across the resistor is. Now, we could do that, that's fine, and if you know how to do that and you want to do it, do it. But for me, with the information that we've got, this is easiest because we have the I, we know what I is, and we know what R is. Now I is 0.19, so we square that and multiply it by 1200, which was our R. You should remember true power is our resistive power, so when we use this formula, we'll use the actual resistance, not the impedance or the capacitive reactance. And that gives us a total power, true power of 43.32. So that gives us two sides of our impedance triangle, power triangle rather. Apparent power and true power. So that's hypotenuse is the apparent power, and true power will be the bottom horizontal side. So then working out the reactive power, the easiest way to do that will be using Pythagoras again. So Q equals the square root of S squared minus P squared. We substitute our values here that we've worked out for S and here that we've worked out for P, and that gives us a result of 5.75 volt amps reactive VAR. And here is my power triangle, nice and to scale this time. I got better at making these triangles as it goes on, so you'll notice this one still looks a bit odd, the next one is better again. So I've labelled it there with my S, Q and P, and I've also put the angle in there. Notice that with a fairly low value of reactive power, we obviously have a very narrow angle. That would also mean we have quite a high value of power factor, which we'll go into shortly. Power factor being a ratio of P over S. P divided by S. Okay, example number 3. 25 kVA single phase motor has power factor of 0.8 lagging. Just as an aside here, when somebody gives you a power factor and they say it's 0.8 or 0.6 or something like that, if they don't say it's leading or lagging, then it's lagging. Lagging power factors are far more common than leading power factors because inductors are things that we have in circuits like motors and ballasts, whereas capacitors we don't really put them in circuits unless we need them for power factor correction. So our power factors are always lagging unless somebody told us otherwise, and that would be a strange situation. We have a power factor of 0.8 lagging. We're going to connect a 10 kVA capacitor for power factor correction. When you calculate the input apparent power in kVA and the power factor of the input circuit, of the improved circuit. So what we're saying is we have a 25 kVA single phase motor. We're going to add a 10 kVA capacitor. We want to calculate the apparent power and the power factor after we've put that capacitor in. The apparent power before we put the capacitor in is 25 kVA, right? Because that's the power that we're given. So obviously we're going to have to go through a number of steps before we can work out that apparent power, the apparent power after we've put the capacitor in. So let's have a look. First thing we should do is probably work out our power triangle for the existing circuit. So I'm going to work out my true power. Give the values that I've got, that seems the most logical step. Now we know our formula for power factor is P over S, true power over apparent power, and therefore if I rearrange that formula for P, it's going to be P equals S times power factor. We know what our S is, that's 25 kVA, it says it up here. So that's 25,000, we know what our power factor is, it says it up here, 25,000 times 0.8. So our true power is 20 kilowatts. And then to work out the new power factor, first we must work out the reactive power of the existing circuit and then add the capacitor. So reactive power is obviously going to be the third side of our triangle, so we're going to use square root of S squared minus P squared again. I'm not going to go through that in detail. If I've used the formula before, I'll skim through it. So that gives us a value of a Q value of 15 kVAR, 15 kilovolt amps reactive. So then we're going to add a 10 kVAR capacitor. So that 15 kVAR Q is an inductive value because we have a lagging power factor. So we're going to add a 10 kVAR capacitor. That's going to improve the power factor by counteracting that lag. So that means that our new Q, the new value of Q, will be the old value, the inductive kVAR, minus the capacitive kVAR. Because the one is going in one direction, one is going in the other, so they counteract each other. So then our new value of Q is simply going to be 15 minus 10. So that would be 5 kVAR. Our P remains the same. So now we've got the Q, so that's one side of our new power triangle after we've put the capacitor in. Our P will remain the same. The resistive power doesn't change. We haven't added or removed any resistance from the circuit. So our P stays the same. That's our true power. So that means we've got for the new power triangle, for the new circuit, I have two sides. I have my Q side is 5, and my P side will be the same as it was before. So if I go back up here, I see that was 20 kilowatts. So my two sides are going to be 5 and 20, and I can then use that to work out my S, which is the hypotenuse. So square root of P squared plus Q squared, 20 squared plus 5 squared. So my S, my new S, as it says here, right over here, calculate the input apparent power of kVA of the improved circuit, 20.62. So notice that after we've added in the correction capacitor, our input power has gone down. 25 kVA motor, the input power has gone down to 20.62, which is a good thing, right? That means that we are consuming less power, but we're going to get the same value out of it because the same motor is going to operate. The motor will still operate, it's just that we're not drawing as much current and therefore we're not paying for as much power. So then I need to work out my new power factor, which is pretty easy. Power factor equals P over S. We've worked out what all those values are. Our P was 20 kilowatts. Our S, the new value of S, was 20.62, and therefore 20 divided by 20.62 is 0.97. Obviously a very high power factor. The highest power factor you can have is 1, because that's a ratio there. The true power can't ever be more than the apparent power. So therefore 1 is the highest power factor we can have, so 0.97, otherwise known as 97%. You could refer to that as 97% efficient. Example number 4. I missed the number there. No, that's number 3. Example number 4. Cool. Making good progress. A load draws 10 amps from a 230 volt 50 hertz supply. Calculate the capacitor required to improve the power factor from 0.6 lagging to 0.9 lagging. Okay, so we're only looking for one answer here, but if we think about it, we're going to have to go through a number of steps to get from 0.6 power factor up to a 0.9 power factor. We're going to have to figure out what the capacitor is going to be. The first thing we're going to need to do is construct a power triangle. So we need to find the values for S, P, and Q, apparent power, true power, and reactive power. S is easy because S is our total apparent power, so that's just going to be total voltage times total current. V times I, 230 times 10, 2,300 volt amps. P is pretty easy. P is our ratio. P is relative to our S, apparent power, and our power factor. We know our apparent power, we just worked it out. And we know our power factor, it's given. So P equals S times PF. True power, one of the ways we can work out true power is apparent power times the power factor. So P equals 2,300 times 0.6, which gives us a value of 1,380 watts. And then to work out Q, again, pretty straightforward. We can use this Pythagoras, S squared minus P squared. So that's our hypotenuse and our adjacent side, or the horizontal side. So that gives us a value for Q of 1,840 volt amps reactive. And here's our power triangle here. Note this is a pretty poor power triangle because my true power at the bottom, that's the power I'm using, 1,380 watts, is pretty small compared to the 2,300 apparent 2,300 volt amps apparent power, because that Q is so high. So what we would want to do is add a capacitor to reduce that down, and obviously that's what we're about to do. Again, note that this triangle is to scale, and when you're drawing your triangles in your test, you will need to draw them to scale. I don't need them to be any more complicated than this. Just have the 3 labels on there. Label the angle if we have the angle, and but make sure that they are to scale. The angle should be the correct angle. The side should be the correct lengths. So, moving on, P will remain the same. Again, we haven't added or taken away any resistance, so on our new power triangle and our new circuit with the capacitor, the P will be the same, the true power will be the same. So if we were to change the power factor to 0.9, our S will change because power factor is the ratio of true power to apparent power. So I can then use that to work out what the S is going to be for my new circuit, because the new S with a power factor of 0.9, power factor equals true power divided by apparent power. If I rearrange that formula to make it about apparent power, it will be S equals power S equals P, true power, over power factor. And I have those numbers. 1,380 watts is our true power, and 0.9 was our new power factor, which gives me a new value for S of 1,533.33 volt amps. And then we can use Pythagoras to work out the new value of Q. Once again, Q equals the square root of S squared minus P squared. There are the numbers there that we've just worked out. That's our new S. P hasn't changed, gives us a Q value of 688.35. So our new power triangle looks like this. Notice that although my triangles are one is bigger than the other, they're still to scale, that the angle has now dramatically reduced, and the difference between our true power and our apparent power has also dramatically reduced, which is a good thing. Again, that means that we are paying for this much power but only using this much power. It's still not ideal. I don't want to pay for more than I'm using, but it's much better than we had over here where I'm paying for this much power and only using this much power. So now we need to work out how much capacitive power is required to bring the Q down to 688.35. So we worked out that that's the Q that we need for our power factor to be 0.9, but that doesn't tell us what capacitor it is. In fact, it doesn't even tell us what the Q of that capacitor will be. So we need to work that out. Q required will equal the old Q minus the new Q. Okay, so our old Q was 1,840, we have that over here. Our new Q to get the power factor of 0.9 will be 688.35. So that means we need a capacitor that is 1,171.65 VAR. So now we know how much power our capacitor will be. We need to work out what the capacitive reactance and the capacitance. First we'll need to know the capacitive reactance, that is the resistance provided the capacitor to give 1,171.35 VAR. Q is a type of power, so we can use the same formula as we would use for power. So power in Ohm's law would be P equals V squared over R. We're going to use Q. We already know our voltage, and our R is going to be QC, right? XC, that's our reactor, our capacitive reactance. That's the resistance that we're going to use. So if we scroll down, so we substitute in QP and XC for R. So that means Q equals V squared over XC. Exactly the same formula. Instead of power equals V squared over resistance, it's going to be reactive power equals V squared over capacitive reactance. So we need to, that's all well and good, but we're actually trying to work out the XC. We know the Q, we know the V squared, we don't know XC, so we need to transpose this formula so we can find out what XC is. We already know what Q and V are. So if we transpose the formula, we'll find that we've got QC equals V squared over Q. Did I say QC? XC equals V squared over Q. And our V squared is 230 squared divided by 1171.65. That's our Q that we worked out earlier. Well, that's our required Q of our capacitor. So that gives us a value for XC of 45.15 ohms. Now we can work out the capacitance that would give us 45.15 ohms of capacitive reactance. We've used this formula before to find XC. There it is. XC equals 1 over 2 pi FC. We should all be familiar with that. We've used it heaps of times. We already know what XC is, so we need to rearrange the formula to find C. And all I'm doing here, if you're wondering how I'm rearranging the formula, if you don't care how I'm rearranging the formula, don't worry about it, because you can just use the formula I've given you. If you are wondering, just remember what I've done. To move the C from the bottom on the right, I need to move it to the top on the left. To remove the XC from the top on the left, I need to put it on the bottom on the right. So they're just switching places. I can just switch places because XC is on top left, C is on bottom right. I just switch them over. So that means C will equal 1 over 2 pi F times XC. We substitute in the values that we know, which is the frequency that was given in the original question, and XC, which we've just worked out, is 45.15 ohms. So then we get C equals 1 over 2 pi times 50 times 45.15, 50 being the frequency, 50 hertz. And that gives us an answer of 70.5 microfarads. What does that mean? That means that if I wanted to improve the power factor of the original circuit from 0.6 to 0.9, I would wire in a capacitor of 70.5 microfarads, and that is going to improve the power factor. We now have a power factor of 0.9. Example number 5. An industrial load which uses a 120 volt 60 Hz supply has a 1000 microfarad power factor correction capacitor. The measured power of the circuit is 23 kilowatts with a power factor of 93%. Calculate the power factor with the capacitor removed. So now we're going to do it the other way around. We've now got a capacitor in there, and it's asking us to work out what the power factor will be if we took that capacitor out. Before we can do anything, we will need to know the value for Q in the circuit with the capacitor in it, so in its current state. The best thing to do is to construct a power triangle. And if you take anything out of this, just build a power triangle. For every question like this that you see, put it together a power triangle. It's going to make your life easier. So we know that P equals S times the power factor. We've been given the power factor, 93%. We've been given our apparent power is 23 kilowatt. So 23,000 times 0.93 gives us a P of 21,930 watts. That's the second side of our power triangle. The first side would be 23,000, the second side is 21,930, and then we can use those two sides, and you should be getting familiar with this formula by now because we'll use it in nearly every question. Q equals the square root of S squared minus P squared. Q then equals 23,000 squared minus 21,930 squared, and the square root of that result, which gives us a Q of 8,453.87 VAR. So the power triangle for the original circuit looks like this. Again, this is to scale, trust me it is. S 23,000, Q 8,453, P 21,930. It gives us a phase angle, by the way, of 21.08. It wasn't asked in the question, but I'm just putting it in there because I make it interesting for you. So if we take out the capacitor, that's going to increase the value of Q. Remember, we've put that capacitor in to correct our power factor, so that has brought the Q down. To find out how much, we need to work out the reactive power drawn by the capacitor. So we're going to take that capacitor out. Once we do, then whatever reactive power is drawn by the capacitor will then be added on to this to give us our new reactive power. So we need to find out the reactance of the capacitor, or capacitive reactance of the capacitor. And we use the standard formula, XC equals 1 over 2 pi FC. We know what the capacitor is. It was 1,000 microfarads, we were told that. We know what the frequency is at 60 Hz. So then we just substitute those numbers into the formula. 1 over 2 pi times 60 times 1,000 times 10 to the negative 6. That's our, remember 10 to the negative 6 is our conversion of microfarads. Gives us a value of 2.65 ohms. 2.65 ohms of reactance in that capacitor. Then to work out the reactive power generated by that capacitor, we use the formula, back up to the top, Q equals V squared over X. Remember, this is the same one as we looked at before. Q is our reactive power, volts squared over X being our reactance. Remember, this is exactly the same as Ohm's law formula, P equals V squared over R. We're going to go Q equals V squared over X. Our V was 120, so we square that and we divide by the X that we've just worked out, the XC. Remember, the C on our X is just to note that it's capacitive, and L would note that it's inductive, but if we only have one type, we can just call it X if we want to. So 120 squared over 2.65 equals 5,433.96. So that's the reactive power just of that capacitor. So if we remove the capacitor from the circuit, then we're going to add that QC, the power, the capacitive reactive power of the capacitor onto our existing value for Q. So our new Q would be the old Q plus the QC of the capacitor. So new Q will be 8,453.87 plus 5,433.96. That was the Q that we had before, and this is the Q of the capacitor. So that gives us a new Q value of 13,887.83 VAR. Now that we have this value, we can build a power triangle for the circuit without the capacitor, and then use that to give us the power factor. True power doesn't change. Again, we haven't changed the resistance of the circuit. We haven't added any resistance or removed any resistance. So we can work out our apparent power using Pythagoras. S equals P squared, which doesn't change, plus Q squared. We've got that new value, and that gives us a figure of 25,503 volt amps. That's our new value of S after we've taken the capacitor out. So our new power triangle looks like this. Notice that our angle has increased because our Q has increased. Our power factor is getting worse. Our S has increased, so even though we're only using the same amount of power, we're paying for more power because we've made the power factor worse. We can use this formula to work out. Our power factor. Power factor equals P over S. So it's just the ratio of true power to apparent power. We have those values. 21,930 was our true power. 25,503 was our apparent power, and therefore our power factor is 0.84. So taking out the capacitor has changed from a power factor of 93%, 0.93 that we had originally, took the capacitor out, and it's brought our power factor down to 0.84. It's gotten worse. Example number 6. A 10 kVA load of 0.2 lagging is connected to a 230 volt 50 Hz supply. Calculate the supply current and true power of the load. Also calculate the capacitor required to improve power factor to A 0.9 and B unity. Unity is a power factor of 1. So let's go through this set. So the first couple there should be pretty straightforward. Calculate supply current, I equals S over V. So apparent power divided by voltage, power divided by voltage. So we've been given the apparent power. It was 10 kVA, 10,000, divided by the voltage 230 equals a current of 43.48 amps. Now true power will be apparent power times the power factor. We've got a power factor here, we were told it was 0.2. So 1,000 times 0.2 is 2,000 watts. We use Pythagoras to work out Q and then create our power triangle. Q equals square root of S squared minus P squared gives us a Q value of 9,797.95, and here is our power triangle. Note how strange that looks because we have a very poor power factor. Our power factor is 0.2, so that angle is going to be massive at 78 degrees, and we have a very high value of Q compared to our value of P. We also have a very high value of S compared to our value of P. So we're only using 2,000 watts. We're only getting 2,000 watts of value, but we're paying for 10,000. So that's really bad. We need to fix that. So we're going to change the power factor from 0.2 to 0.9. Again, the easiest way to do this is to build that power triangle. So our new apparent power, after we've changed the power factor, will be our true power. That doesn't change. We haven't added or changed any resistance. The true power divided by our new power factor, which was 0.9. Going over to the right hand column here, gives us an apparent power 2,000. True power divided by power factor 0.9. So our new apparent power will be 2,222.22 volt amps. And we complete our power triangle by using Pythagoras and go Q equals square root of S squared minus P squared, which gives us a Q value of 968 volt amps reactive. So our new power triangle looks like this. That is still to scale. It's a much smaller triangle, but it is still to scale. So we've got our angle from 78 degrees now down to 25.82, which is much better. We're now only paying for 2,222 volt amps of power for the 2,000 that we're using. So things are looking much better with this power triangle. So the capacitive power required to reduce the Q down to the above, down to 968, will be the old Q value minus the new Q value. So our old Q was 9,797.95 minus the new value 968 means that we need to connect the capacitor, we need to connect the capacitor with a VAR value of 8,829. Now we work out the capacitive reactance and then the capacitance of that capacitor to give us a value of 829 VAR. So Q equals V squared over XC. So we're going to need to work out our XC. We've got our Q, we've got our V, we need to work out XC. So we transpose that formula. XC equals V squared over Q. 230 squared over 8,829. Remember that's our Q value of the capacitor that we're going to put in. Gives us a value of 5.99 ohms. To work out our capacitance, we're going to use this formula here. X equals 1 over 2 pi of C. just like before, we're going to have to transpose that formula. So we're working out C, because we already know our XC. We don't know what the C is, so we transpose it. So it will be C equals 1 over 2 pi F times XC. And we substitute in the values that we know. 50 Hertz was our frequency, 5.99 was our capacitive reactance, 5.99 ohms. And if we do that formula, we should come out with a capacitive value of 531 microfarads, which is a big capacitor. Okay, so that was part 2 of the question. Part 3 was to do the same thing, but for unity power factor. That is power factor equals 1. We can't create a power triangle, because if our power factor is 1, then our Q must be 0. Why? Because power factor equals true power over reactive power. So if the power factor is 1, then the P and the S in this formula must be the same. I don't know what number they are, but they have to be the same. If power factor is going to be 1, then the P and the S must be the same number. And then, so those are two sides of our triangle. So if my horizontal side of my triangle is the same as the hypotenuse, then it's not even a triangle, it's just two parallel lines. So we don't actually have a triangle. Q is 0. S and P are the same number, Q is 0. But to have a power factor of 1, therefore, we must add a capacitor into our circuit that has the same value of Q as the existing inductive Q in the circuit. So the Q going in the up direction must be now counteracted by an identical value of Q going in the down direction. That means that my Q, my inductive Q and my capacitive Q will cancel each other out to leave me with a Q value of 0, which is how I'm going to get that unity power factor. So the original Q in the circuit was 9,797.95 VAR. So we follow the process of working out our XC and then C for a capacitor that is exactly equal to 9,797.95 VAR. So again, we use the same formula, transpose for XC, substitute in the values that we know, gives us an XC's out value of 5.4 ohms. We then use the formula for XC, 1 over 2 pi FC, transpose it for C, C equals 1 over 2 pi F times XC. Back up to the top here, which gives us, we substitute in 50 Hertz and 5.4 ohms, gives us a capacitor of 589 microfarads. So that means that if we put a 589 microfarad capacitor into our circuit, then the power factor will now be unity, which means that our apparent power and true power are the same. So we only pay for exactly the power that we use. Example number 7. We've got 11 total, just so you know. So 7 out of 11, we get in there. In a series RL circuit supplied with 209 volts, the current is measured as 7 amps with a phase angle of 49 degrees. Calculate the apparent power, true power, and reactive power of the circuit. When you see a question like this in your test, you are going to have to draw a power triangle in there as well. So take note of the power triangles I'm creating along the way. So apparent power is easy, right? S equals V times I, supply voltage times total current. We've got that 209 volts is 7 amps, so that's 1,463 volt amps. True power then, so now we've got an angle, and we know one of the sides of our power triangle, but that's all. So now we're going to have to use trigonometry. We're going to use car because cos of the angle equals the adjacent over the hypotenuse, right? So the true power is the adjacent side, that's the horizontal side, and apparent power is the hypotenuse. So we know our angle and we know the apparent power. That means we've got the angle, we've got the hypotenuse, so we can work out the adjacent with the car. So cos of the angle equals P over S, true power over S, which is adjacent over hypotenuse. We transpose that for P, so P equals cos of the angle times S. So that would be cos 49 times 1,463, which was our apparent power up here. Gives us a true power of 949.8 watts. And then for our reactive power, we just use the Pythagoras again. I've said that 100 times already, I won't say it again. To get a Q of 1,103.98 VAR, which gives us a power triangle that looks like this. Pretty straightforward. Example 8. in a series RC circuit supplied with 236 volts. The current is measured as 21 amps with a phase angle of 26 degrees. Calculate apparent power, true power, and reactive power of the circuit. Exactly the same as the previous question. Apparent power will be our V times I. We've given the voltage, we've been given the current, so it's 236 times 21, it's 4,956 volt amps. True power, the same as before. Cos of the angle equals adjacent over hypotenuse, therefore cos of the angle equals true power over apparent power. We transpose it for P. Cos of the angle, power P equals cos of the angle times S. So cos 26, we're given the angle of 26 degrees, times 4,956, we worked out the apparent power, gives us true power 4,454.4 watts. Reactive power, we now have the two sides of the triangle, so we use Pythagoras to work out a third, and it is 2,173.44 VAR. And our power triangle looks like this. Note again that this is to scale, and your power triangles will also need to be to scale, please. Example number 9, 3 to go. An RL circuit, so a resistive and inductive circuit, supplied with 296 volts. The current measured is 11 amps with a phase angle of 66 degrees. Calculate the apparent power, true power, and reactive power of the circuit. Also calculate the capacitive reactive power, so the QC, required to improve the phase angle to 18 degrees. Apparent power, we know that one now, S equals V times I, so that's 3,256. True power, we're going to use the same trigonometry because we only know the one side of our triangle and the angle, so we follow the same as we've done for the last two questions, and that was cos of 66, that was our angle, times 3,256, which is our apparent power, gives us a true power value of 1,324.33 watts. Our reactive power will be using Pythagoras to find the value of the third side, 2,974.51. Okay, and that's our power triangle there. Pretty simple, same as the last two questions. We should be fairly familiar with that now. Now it gets a little bit tricky. We need to work out the QC to improve the phase angle to 18 degrees. To do that, we need to know what the Q will be when the angle is 18 degrees. So we're going to create a new power triangle. So using trigonometry, we know the angle, that's going to be 18 degrees. We know the adjacent side, that's the true power, because true power hasn't changed. We haven't changed the resistance in the circuit, so our true power stays the same. That means we can use TOA to work out the reactive power. The reactive power being the opposite side in our trigonometry formula. So tan of the angle equals opposite over adjacent, and therefore tan of the angle equals Q over P. Q is the opposite, P, true power, is the adjacent side. Transposed for Q, Q equals tan of the angle times P. Tan of 18, that's our new angle that we're working out, times 1,324.33 was our true power, gives us a Q value of 430.3 VAR. So the QC required to bring the Q down to 430.3 will be the old Q minus the new Q. So that's 2,974.51 minus 430.3. That was our old Q value, that's our new Q value. So required QC, and that was the question that was the question that we were asked. What is the capacitive power required to improve the phase angle to 18 degrees? 2,544.21. Example 10. A 9 kVA single phase motor connected to the MEN system has a power factor of 0.53 lagging. A 6.5 kVAr capacitor is connected for power factor correction. Calculate the original input current of the circuit. Also calculate the input apparent power in kVA, current and power factor of the improved circuit. Okay, so multi-part question here. Right, so the first thing I'll say, the question says MEN system, so we'll assume that the voltage is 230 volts and the frequency is 50 Hz. To get original input current, I equals S over V, so current equals power divided by voltage, 9,000, which we were given, 9 kVA, divided by 230 volts. That was our standard MEM power, gives us a current of 39.13 amps. To work out the apparent power of the circuit after the capacitor is added, we first need to know the apparent power and reactive power of the circuit before the capacitor, so we will create a power triangle. We need to work out true power first, so we'll use apparent power times power factor because we know what those two things are. It gives us 4,770 watts, and our Q value will be the Pythagoras of those two other sides, which is 7,631.98. And here's our power triangle for that. S equals 9,000, here's our Q value, here's our P value there. No, that's a pretty big angle there, so that's going to be a poor power factor. Well, it's 0.538. The value for Q after we have added the capacitor will be Q, and the Q that we're given minus the capacitor VAR. We were given the capacitor VAR, we were told it's a 6.5 kVAR capacitor, so 6.5 kVAR means 6,500 VAR. So our new Q will be the 7,631 that we have here, minus 6,500, which gives us 1,131.98. Because P will remain the same, we can now use P and the new value for Q to work out the new apparent power. We've got those two sides. So S being apparent power is our hypotenuse, so square root of P squared plus Q squared, that's true power and reactive power, gives us an S value, apparent power 4,902.48, and here is our new power triangle. This is what we were asked to work out, the apparent power of the circuit after we put the capacitor in. And then we were asked to work out the current of the new circuit. So here's our new power triangle here, and our new S, our new Q, and our P was the same. Notice that our angle is much smaller and our Q side is much smaller, and we have a much better power factor. Current in the new circuit, the same formula will be the same, apparent power divided by voltage, 4,902.48 divided by 230, so our new current will be 21.32. Notice if we go back over here and we see that the original current was 39.13. We've almost halved it by adding that capacitor in. So this is the value. This is one of the values of improving our power factor. Our power factor in the new circuit, power factor equals P over S. It's a ratio of true power to apparent power. So that would be 4,770 divided by 4,902.48 gives us a power factor of 0.97, 97% power factor. So that's very good. And question 11, which I think is the last one. Let me just check. Yes, there we go to 11. A load draws 11 amps from a 232 volt 45 hertz supply. Calculate the original apparent power in kVA of the circuit. Calculate the capacitor required to improve the power factor from 0.41 lagging to 0.73 lagging. Also calculate the new current. So apparent power, what have we got here? We have okay, so I have, as I said at the start, I thought it's possible that I've made a mistake, and it appears that I have here. So in my haste, it looks like I've used the wrong formula. So I've tried to go S equals P over power factor, but we don't have any of those numbers. We don't have we don't know what our true power is. What I should be doing is 11 amps times 232 volts. Volts times amps equals our apparent power. So I can tell you that answer is correct. 2,552 volt amps is our apparent power. Ignore the working out that I've done before that. It should be V times I. To work out a capacitor required to improve the power factor to 0.73, we need to know the current reactive power Q and what the reactive power will need to be when the power factor is 0.73. We can work out the capacitive power required, then we can work out the capacitive power required and the capacitive reactance from that capacitive power, and finally use the capacitive reactance to work out the capacitance. That's a mouthful. Now true power will be S times PF, power factor. Our power factor we were given was 0.41 and our apparent power was 2,552. That gives us a true power of 1,046.32 watts. The reactive power of the existing circuit, well, we've now got the two sides. We've got the 2,552 is the apparent power, 1,046 was our adjacent side, the horizontal side. So we use Pythagoras, which gives us the third side. Q is 2,327.64 VAR. And yeah, I should have a triangle, here it is, and that's our power triangle there. So then after I've changed the power factor, I can work out the new apparent power. So we're going to change the power factor, remember, up to 0.73. P doesn't change, true power doesn't change. I haven't added or subtracted any resistance, so it will be true power divided by power factor gives me apparent power, which is 1,433.32. That would be my new apparent power. The Q after my power factor improvement then will be the new S was one side and the new P is the other side, and use Pythagoras to work out the third side, which is my new Q, and there's my new power triangle here. I've got my new S, my new Q, and P is the same. So the capacitive power required to bring the Q down to 979.6, which is the value here, will be the old Q minus the new Q. So if I had the old Q was 2,327.64, that was our original calculation, and then my new Q needs to be 979.6. That means that minus that equals a capacitor of 1,348.04 VAR. That's what I need out of my capacitor to bring my Q down to this value here. So then we're going to work out the QC of that capacitor, a capacitor that's 1,348 VAR. Q equals V squared over XC. We transpose that formula for XC will be V squared over Q. We know what our Q value is, 1,348.04. That's the Q value of our new capacitor. Voltage was 232, so we square that, gives us a value of 39.92 ohms will be our capacitive reactance. We're going to look at the formula XC equals 1 over 2 pi FC. We transpose that formula to be about C. C equals 1 over 2 pi times F times XC. Substitute in the values that we know. 45 hertz we were given. 39.92 was our value of XC that we worked out. It gives us a capacitor of 88.6 microfarads. So that's the capacitor we need to put in to improve the power factor. Our new current then, we'll ask the final question, we'll ask the current of the new circuit will be apparent power divided by voltage. Our new apparent power was 1,433.32 volt amps. We divide that by voltage to give us 6.18 amps. And that is the end of that. If you got through that and it's still making sense, well done. I feel like it probably just doesn't make much sense to me anymore. Nevertheless, alright, next step is if you go back to the Canvas page now, you should there will be a link there with practice examples, and I've created a practice quiz in Canvas with examples just like this. In fact, most of them will be identical to this, we just have different values, so it's your turn to go through and work those out. Once you've got that nailed and you believe you can do that 100%, then you're ready to go for that test. If you're struggling with those practice examples, you need to get in touch with me and we'll figure out what to do next. All right. Thank you very much, as ever, for your time and attention.